Welcome to the satellite communication course. Today we will learn few numerical on this satellite orbits and orbital parameter. So you may write down here, find the velocity, find the velocity of a satellite in the orbit at an altitude of 35786 kilometer. Assume the average radius of Earth assume the average radius of Earth as 6370 kilometer as 6370 kilometer. Now here that altitude is given, that is about altitude 35786 kilometer, that is given, and the earth radius, that is given 6370 kilometer. Now here we need to know about what is the velocity of a satellite, that is velocity of satellite, and that velocity of a satellite is depending upon that what will be the radius there and what will be the gravitational constant, and that is velocity v is equal to what? We have the gravitational constant u, and that will be the radius. This radius is from the center of the earth, so we need to consider that this gravitational constant divided by whatever the radius of earth and this altitude. This way we can find out. So if you put that all the values here, and for this radius of the earth it is given here, that altitude is given, it is here, but this constant, for this constant, so this is about a gravitational constant, that will be becomes what? 3.986 into 10 to the power 5 kilometer cube by s square. Okay, now this you can put that gravitational constant here, this value 3.986, and this, and we have a Re plus Ra. After solving, you'll get that the velocity is equal to 3.05 kilometer per second. Or we can calculate that this velocity in terms of hours also. So how much will be the kilometer per hour? So even you can calculate it by using this. Right now this is about this velocity is about in terms of a second here. So you can calculate even in terms of a kilometer per hour. So that approximately 11069.8 kilometer per hour. That is about the velocity. Now next one we can this one is about this equation, that velocity, that is that related to the Kepler's first law. So what is the Kepler's first law? If you see that in the Kepler's first law, that is related to the body rest. Okay, body at rest continues to be rest there, and whatever the we can consider that the velocity according to this particular body means whichever the satellite moves around that Earth, whether it will be in an elliptical manner or whether it will be in a circular manner. Just like we consider a satellite that is moves around the Earth in an elliptical orbit. So in that case, That Kepler's law is what? That is a belongs to the law of orbit. Okay, means what we can say that a path of the satellite, it will be elliptical. Okay, the satellite is moving around the Earth. It will be elliptical, having the elliptical orbit, and the Earth that will be lying at the one of the focus here. So that is a focal point. Here we can say that is about the Earth here, and this one is the satellite. That is about a law of orbit. Means path of every planet that will be the elliptical. Okay, that will be the elliptical there. So in the case of if you consider that planet, then we have to consider that is about a sun is at the center there. But right now we have say that a satellite is move around the Earth in a elliptical fashion with a focus. Okay, some particular point is nothing but a focus there. So in that case, that particular focus point is nothing but the Earth there. That is about the Kepler's first law. Then according to the Kepler's law, we have the another equations there, another form numericals. Next is about next numerical using the Kepler's third law. Using the Kepler's third law, find the altitude. Find the altitude of find the altitude of geostationary orbit. Okay, find the altitude of a geostationary orbit. Find the altitude of geostationary orbit. Assume that the mean radius the mean radius assume that the mean radius of Earth as 6378 6378 kilometer, and the mean tidal ray and the mean tidal ray as 86,164.1 second, and Kepler's constant, and the Kepler's constant is 3.986 into 10 to the power 5 kilometer cube by s square. Okay, that a Kepler constant, that is nothing but a gravitational constant that we say earlier here. Now our aim is about to find out use this Kepler's third law. What is the Kepler's third law? That is t square is equal to what? Directly proportional to the r cube. Okay, that is about a Kepler's third law. Whatever the time period required, okay, for the given satellite for the rotation there. So according to that, a third law is there. Means what? We can say that a square of a time period t is equal to what? A square of a time period of a satellite in orbit that will be proportional to the r cube. Okay, that is will proportional to the distance of the orbit from the center of the earth there. And that is nothing but what? T is equal to t square is equal to r cube there. Now we use this law, and we consider that equations for this radius, okay, from the center of the earth. So using this law, so t is what? That t is equal to what? That is about the period of your evaluation, and that period of your evaluation is given in terms of how much is the circumference of this that particular satellite or that orbit, or what we can find out using that uh, velocity. Okay, that time period means total circumference divided by with respect to the velocity. So you can find out the total circumference, that is twice by r, by velocity of the satellite. And then this velocity, you know that it is equal to what? Twice by r. Velocity is equal to a, that is a general equation of what? A gravitational constant and a r here. And if you further solve it, you'll get that twice pi r is to 3 by 2 divided by u raised to whatever the 1 by 2. Or we can directly say that t square is equal to 4 pi square pi mu raised to what we can say r cube. Okay, that is we consider in terms of a t square. So mu get, if a 1 by 2 will get cancelled. So here we have a 4 pi square by mu into a r cube. Now find the altitude of its geostationary satellite. Okay, now our aim is about to find the altitude of a geostationary satellite. So in that case, we need to consider that altitude, that r is nothing but what? Re plus h. R is equal to what? Re plus h. So we can calculate for this r is plus h here, and then the time period we have. Okay, the time period we are getting. That is time period is about a 86164.6. Okay, 1 second. So if you put that time period here, and this is as usual Re plus h here. So h we know that whatever the altitude we know that here, that it is given that the mean radius of the earth is given, and our aim is about to find out the altitude. Now this one is a factor. If you put here Re, that is 6378, and this mu is constant, that is 3.986. This one is about a constant here. Okay, put that t, put that mu, put that Re here. So you will get that what will be the value of this altitude. And after solving this altitude, we are getting that is about 35786.1 kilometer. Okay, after solving this, you will get the altitude. Next one, a satellite. We you can say that it is orbit. We can have that satellite is in a low orbit. Okay, so we can write here a low orbit satellite. A low orbit satellite has an altitude of 400 kilometer. Find the period. Find the period of the satellite. Find the period of the satellite, assuming assuming the radius of Earth, assuming the radius of Earth as 6.37 to the 10th power 6 meter, and mass equal to mass equal to 5.98 into 10 to the power 24 kg. Now, in this case, if you see this equation, that altitude is given here. We have the altitude is given, that is about a h. Okay, given for data we have h is equal to 400 kilometer is given. Now our aim is about to find the radius of this satellite. Means we can find out the r here. So r is nothing but what? R is equal to Re plus H. R is equal to what? Re plus H. We can consider that find the period of the satellite. Okay, not really. So we can consider that we need to find out a T here. Find the period of satellite and the radius of the earth is R is equal to Re plus H. So T is equal to what? As we say earlier that T square, okay, this is about Kepler's third law. K plus T square is directly proportional to the R cube here. Okay, T square is directly proportional to the R cube. Now the same thing we have used here. T square is directly proportional to R cube. Means T square is equal to what? 4 pi square by mu in bracket into R cube. So means T square is equal to what? 4 pi square by mu raised to R cube. Okay. Or we can say that even if we wanted to calculate in terms of only a T, so that becomes what? Twice pi by under root of a mu R raised to 3 by 2. Okay, you can directly calculate only the T also. Okay, that is no matter. But we can use this equation to obtain that T and R. Okay, so to obtain this T, that gravitational constant is about a 3 point something that we have used earlier. That is nothing but a mu we have considered earlier. That is about a 3.986 into 10 to the power 5 kilometer cube plus by a square. Now we know that mu. Now what is about the R? R is nothing but what? R is equal to Re plus H. And this radius of the earth is given, that is 6.37. If you calculate in terms of a kilometer, 6370 kilometer. Okay. If you obtain here that earth radius, okay, that earth radius, we have written there 6.37 into 10 to the power 6. Even we can write, here it is in meter. So here we can write 6370 into 10 to the power 3 meter or 6370 kilometer. That is about the radius of the earth. So we can write here that R is equal to what? Re plus H is equal to 6370 plus your 400. Whichever the answer we are getting, that will be in the terms of a kilometer. 6770 kilometer. That is about the R. We can put that value of a R here in this equation. Value of this mu here. Then you will get that time period, that T, or we can say that the period of this, find the period of the satellite. Okay, means we will get that the period of the satellite rotating or moving around the earth, and that is T is equal to what? 1 hour. Okay, we say 32 minutes. We'll get that T is equal to 1 hour 32 minutes. Next, we'll see that another one, a remote sensing satellite. A remote sensing satellite is placed in a polar orbit, in a polar orbit with a period of, with a period of 99.3 minutes. Means that is about a one rotation. 99.3 minutes means it is about the one rotation here. Find find the orbital height find the orbital height of this of this satellite and its velocity. Now that given data, if you see that given only it is about a t, and that t is equal to what? 99.3 minute. That m is nothing but a minute. Now we have to convert that minute into a second, then we'll get that 5958 seconds. Okay, that is about the answer in terms of a second we get. Okay, we are. Now we know that Kepler's third law, that Kepler's third law is what? T is equal to twice pi by under of a mu. Okay, because our aim is about to find the orbital height and our aim is about to find its velocity v. Means we need to find out the orbital height, that's altitude, and what will be the velocity. So to find out the velocity, we know that v is equal to what? Under root mu by r here. That is about the velocity equation. But altitude, to calculate that altitude, we can use this orbital period there. Because t is directly proportional, we say that t square, that square of a period is directly proportional to the whatever the distance from the center of the earth, cube of the distance from the center of the earth. So that's why t is equal to what? Twice pi under root of mu into r raised to 3 by 2. That r is nothing but what? R we say that Re plus H. R is equal to what? Re plus H. Now, if you consider this equation here, the t is equal to what? That is 5958 second, and a twice pi, that is about a constant we have, and then there is about a mu, that becomes what? The we have considered earlier 39 something. Okay, 3.986 into 10 to the power 5. Okay, so that's about 3.986 into 10 to the power 5. So that's raised to 1 by 2 into r cube. That r is equal to what? Earth radius. That earth radius is what? We have considered 6370. Okay, you can say that 6370 plus altitude raised to 3 by 2. Okay, this one is a raised to 3 by 2. 6370 plus h raised to 3 by 2. Now this one is about a factor here. 6370 plus h raised to 3 by 2 is equal to, we have the whole term here. These are about the all whole term. So you will get that particular term while solving, that becomes a 598674.6 here. And then after solving, you will get that h is equal to 671 kilometer. That is about the answer. H is equal to 671 kilometer. Now next is about to find the satellite. This one we have obtained that orbital height. Now our aim is about to find out the velocity of the satellite. Now that velocity of a satellite, that is v, is equal to what? Under root of a mu by r, and that becomes is equal to what? Mu by re plus h. We know that earth radius. We obtain that altitude, that 671 kilometer here, and this mu is nothing but what 3.986 into 10 to the power 5. Okay, if you consider here that velocity is equal to, that is 3.986 into 10 to the power 5. That's about a mu here. And then RE, that earth radius, we have to consider, that is about a 6370 plus 671. Okay, that is about the RE plus H here. So we can calculate that, and after solving, we'll get that velocity of a satellite, that becomes a 7.54 kilometer per second. That is about the velocity of a satellite. Okay, V is equal to 7.54 plus this one. Next one, we consider another one. Next, you write down India's first experimental, India's first experimental satellite, Aryabhatta, had had low Earth elliptical orbit, had low Earth elliptical orbit with semi-major axis, with semi-major axis of 6969 kilometer, 6969 kilometer, and eccentricity and eccentricity of 0.00402. Find find the apogee, find the apogee and perigee height, find the apogee and perigee height of this satellite. Now the terms are given, that is about a semi-major axis is given, and that semi-major axis, okay, that about a given data, that semi-major axis is 6969 kilometer. Then eccentricity is 0.0402. Find the apogee height. Okay, find the apogee height. Apogee height is what? That is the distance from what? That is about the surface of the earth. Okay, we can consider that from this surface of the earth to the satellite there. And perigee height, okay, we need to find out the perigee height, that is from the surface of the earth to the satellite. From the surface of the earth means what? It is nothing but a altitude. Okay, that is nothing but a altitude. Or in another way, we can say that a length or a height of the satellite from the surface toward the apogee or toward the perigee there. Now, if you consider the satellite here, that is about the orbit, and this one is about the earth now, and this is about your satellite, and this one is about the center of the. Now, this distance is called as a perigee, and this distance is called as a apogee. Now, this apogee, that is about the height of the satellite, this from the center of the earth to this apogee, that is called as RA. From the center of the to this perigee, it is called as the RP. This RARP is what we can say that radius, or we can say that is about a length. Okay, we can say that a radius, or we can say that is about the length from the center of the earth to the apogee point. Okay, we can consider that from the center of the earth to this opposite point, we can say that instead of that radius word, we can use the distance from center of earth to the apogee point. Similarly, this RP, that is nothing but what? A distance from center of earth to the perigee. Now this distance, that is from the center of the earth to the perigee, or center of the earth to the, okay, that is nothing but we can say a perigee distance. Okay, in another way, some people say that ARA is nothing but what? A apogee distance. RP is equal to what? A perigee distance. Okay, it's like just a distance. Now it's just a distance. Now our aim is about here to find out the apogee and a perigee height. That is height means what? Here, from the surface of the earth to this, that is nothing but what? A perigee height. From this to this, our aim is about to find out the height of the apogee and height of the perigee. Now this one. So means this RA is what? From the center of the earth to this one. RP means what? From the center of the earth to the perigee. But our aim is about to find out the height. This is called as a apogee height. From the surface of the earth to the apogee point. From the surface of the earth to the perigee point. That is height toward the apogee and height toward the perigee. So to obtain that apogee height, we need to find out what will be the apogee and what will be the perigee. And from the RA, if you subtract the radius of the earth, then you will get the apogee height and a perigee height. Then you will get that apogee height and a perigee height. So apogee height and a perigee height is nothing but the distance from the surface of the earth to the apogee point, and surface from the earth to the perigee point. Okay, this line we have to calculate. So to obtain that, we need to calculate that what will be the RA and a RP. Apogee height is nothing but what? A distance from what? From the point from the surface. So that's why we need to subtract the radius of the earth. We need to subtract from the radius of the earth. Its apogee height is nothing but RA minus RE. Perigee height is nothing but the RP minus RE. Now we will calculate here. Okay, we'll see that how this apogee height is to be obtained. So now the given data is A. We have given data is nothing but a semi-major axis, and we have received the another term that is about the eccentricity. Now from this the given data, if you calculate that, okay, if we obtain the equation of the eccentricity, E is nothing but what? E is equal to what? RA minus RP divided by RA plus RP. So that eccentricity is nothing but 0.0042. Sorry, 402. Okay, 0.00402 is about the eccentricity. So from that we can calculate that RA plus RP factor or RA minus RP factor. Okay, either this one or that. One of the factor we can calculate. So that's why we need to know about that semi-major axis A is equal to what? That is 1 by 2 by RA plus RA plus RP. Means exactly this is about a major axis. This one is about the major axis. And for this major axis, there may be a center here. Okay. For this major axis, means this is about a ellipse. In an ellipse, this one is about a major axis. For the ellipse, and this one is nothing but a minor axis. Okay, this is nothing but what? A minor axis, and this one is nothing but a major axis. For this major axis, this one is about a center. Okay, that is about a center of ellipse. And this one is nothing but what? Center of focus. Okay, we can say that this is about a center of ellipse and center of focus or focus of his ellipse here. So semi-major axis is nothing but what? This distance. That is from the center of the ellipse to this apogee point or from the center of the ellipse to the peric point. Means half. Semi-major. That's why this RA plus RP divided by 2 is nothing but this particular fact. So we can calculate that RA plus RP, semi-major axis, RA plus RP means what? For a given ellipse, for a given ellipse, this one is about its semi-major axis. Here we have a center and this becomes a semi-major axis. That's about a here. This A we have to calculate. So this A is equal to what? 1 by 2 RA plus RP. Okay. Because here is we have this center of the earth. So from this to this is RA, from this to this RP. So RA plus RP. A we have to calculate. A is equal to RA plus 1 by 2 RA plus RP. If you solve it, twice of A is equal to what? RA plus RP. So that RA plus RP, because A is given, okay, this A factor is given. So means we can calculate that RA plus RP is equal to 2 into A is what? 6969 kilometer. So we'll get that RA plus RP is equal to 13938. 13938. Okay, that is about RA plus RP. And we know that eccentricity, that equation of eccentricity, this one, A is equal to what? RA minus RP divided by RA plus RP is equal to this one. So we got this RA plus RP, that is 1398. From the eccentricity, RA plus RP we obtained. So we'll get that RA minus RP now. So RA minus RP is equal to what? 0.0402 into RA plus RP. And that RA plus RP we obtain, that is 0.0402 into 13938. We'll get that RA minus RP. After solving, we'll get that RA minus RP is equal to what? 56. RA minus RP is equal to 56. Now there are the two terms. One is about a RA plus RP, another is about a RA minus RP. So if we add these two terms, what? RA plus RP and RA minus RP. If we add these two terms or these two equations, we will get that twice of RA. Okay, RP get cancelled. We'll get that a twice of RA, and that twice of RA is equal to what? That is about a 13938. Okay, and we have the factor is about that RA plus RP and RA minus RP. That is about a 56 here. So RA plus RP, this one is about 13938 plus a 56 here. Solving that, we'll get that RA is equal to, that is about a 6997. So similarly, we can calculate that RP is equal to, okay, we can calculate that RP, that will be is equal to 6941. Once we go obtain the RA, once we obtain the RA here, we can put that RA here. RP is equal to RA minus 56, means 6993 minus 56, we will get that RP. That is about the RP we are getting. Now our aim is about to find the apogee height. That apogee height is equal to what? RA minus whatever the earth radius. RA is equal to what? 6993 minus earth radius is about a 6378 kilometer. So after solving that, we'll get that 619 kilometer. Similarly, we can calculate that perigee height is equal to RP minus perigee height is equal to what? RP minus RE. That perigee height is equal to 6941 minus 6378. So perigee height becomes what? A 563 kilometer. This one is about a perigee height, and this one becomes a apogee height. Okay, apogee height and perigee height. So we obtain. So that is about, we can calculate that a apogee height. So apogee height is nothing but what? A distance from the surface of the earth to the apogee point, distance from the surface of the height to the perigee point. And the apogee means what? Apogee, height and apogee. Okay. Apogee means what? That is the distance from the center of the earth to the apogee. Apogee height or apogee distance. Okay. Apogee distance is from what? That is from the center of the earth to this apogee point. Apogee point. And from the center of the earth to perigee point, that is about the perigee distance. So that distance is from the center of the earth. Apogee distance and perigee distance, both the distances are from the center of the earth. But the height, apogee height and perigee height is nothing but what? It is not a, that height is nothing but it is from the surface of the earth. That height is nothing but the surface of. If the satellite position is there, we need to find out the height. Height is nothing but a altitude in another way. But here we use the word height because we need to find out for the apogee there, apogee height and perigee height. But in the case of a satellite, we are using that word, that is about the altitude of a satellite. Altitude means what? That is from the surface of the earth. Altitude is nothing but what? That is from the surface of the earth. So for a given particular satellite, if you consider that this is about the earth, okay, this belongs to, we can say it is about the earth, and this is about a center of the earth. So this one is nothing but what we can say a radius of the earth. This becomes so then nothing but the radius of the earth. And here is the position of a satellite. This one is about a position of a satellite now. Now from this we need to calculate, from this we need to calculate that height. This is nothing but a height. That is height is from the, or we can say that is about a altitude. You can say that is nothing but a altitude. That altitude is from the center of the surface. Okay, that from the surface of the earth, and this distance generally we consider from the center of the earth. All distances we consider from the center of the earth. Okay, this distance from the center of the earth to the satellite. But generally we consider the altitude, so that's why from the surface of the earth. So all the time. Because surface is not a circular in a shape. So because of that, we need to consider a altitude always. So that is about we can consider here a apogee height and a perigee height. Okay, that's all now.